Okay, welcome back, everybody. So I think the midterm exam is due today at 5 p.m. Most of you have already handed it in. If you have not handed it in, please either email it to us or submit it on the Catalyst Dropbox or slide it under my door by 5 p.m. today. Okay? How many in the room have actually taken the exam so far? How many have not taken it? Okay, just curious. Okay, so remember last time we were talking about numerical differentiation of functions or data? So I just want to put this up from last time. We had a couple of different ways of approximating the derivative. Okay, so this is finite difference approximations to f prime of x. It's kind of an x. Okay, so what were my approximations that we had from last lecture? Forward difference, backward difference, and central difference. Okay, so forward difference was f prime x is approximately equal to f of x plus delta x minus f of x divided by delta x. Okay. Backward difference was f prime is approximately equal to f of x minus delta x divided by delta x. And central is f prime of x is what? Okay, x plus delta x. So I think of my point fx in the center of x plus delta x and x minus delta x, and I take the difference and divide by 2 delta x. Okay, is there anything missing from these expressions?
Error?
The error. Okay, so this is really important to know. We're going to be picking finite size delta x's, right? We can't take delta x goes to 0 like we'd want to. And so these have different errors depending on what the method is. Okay, so what are the method, what's the error for forward difference? Sorry, louder. Ordered for forward difference? Just delta x. Order delta x. Backward difference is also ordered delta x. And central difference is ordered delta x squared. So which one of these is going to be the most accurate method?
Central.
Central difference, right? Because if I make delta x smaller, this error gets way, way smaller, right? It gets smaller like delta x squared. You know, if I could, I'd like to cook up something that had order delta x to the 4th or 6th or 8th. That would be even better, right? It would have even better scaling properties. Okay, any questions about this at this point? So on the next homework, I'm going to, for example, ask you to cook up a second order accurate forward difference scheme. So what types of data would you need to have a second order accurate forward difference? So for a first order accurate, this is called first order because delta x is to the first power. This is second order because it's to the second power. If I wanted a second order accurate forward difference scheme, I would need f evaluated at what points?
Delta x plus delta x.
Okay, so second order forward difference. So I think I heard this. I would still need f of x. I would still need f of x plus delta x. But remember, I'm plugging in the Taylor series for these expressions, and I'm trying to cancel as many terms as I can. And to cancel more and more terms, I need additional data points. I also need f of x plus 2 delta x. Okay? So if I give you these 3 data points, you should be able to cook up a second order accurate forward difference scheme, and you should be able to show why it's second order accurate. And you would show why it's second order accurate by literally computing the Taylor series of these 2 expressions, plugging it into whatever formula you cook up, and showing that you get the thing you want, the first derivative, plus terms that are on the order of delta x squared. Okay, so this is going to be like a homework 4 type problem. Okay. So homework 4 should come out like tomorrow morning sometime. Okay, good. All right, one more point. When we actually have data, so in the last lecture, we cooked up data based on a sine function, right? We took sine of x, and we computed all 3 of these derivatives. But in real life, if I'm getting data, streaming in time, I can't compute the forward difference, and I can't compute the central difference because I don't have future points in time, right? So let's say that I have a vector of data instead of a function. Okay, so I have data x1, x2, x3, ... up to xn. Okay, these are kind of my x values. And for now, let's just assume that these are all spaced delta x apart. But they don't have to be spaced delta x apart. That's just an assumption to make this a little easier. And let's say that I have some function over these values. So I have f versus x. And that means that I have f defined at all of these locations. Okay? So this is, f1, f2, f3, ... fn. And we have this relationship that f, k equals our function of xk. And that equals our function of k delta x. Right, so here this subscript k really means, if all of our delta x's, if all of our points are spaced delta x apart, if x0 is 0, then xk is just k of these delta x's away. Okay, so xk is just k delta x's for evenly spaced data. And so the way I like to think about this is I just have these 2 vectors of data. My boss emails me vectors of data and wants the derivative taken. Okay, my second vector is the function value at all of these points. So I just have these 2 vectors of data. I don't have functions. I have my function evaluated at a discrete set of points. So now I'm going to ask, how do I compute the derivative based on these vectors? How do I compute df dx? What's the best scheme I can use to compute this derivative that we've derived so far? Central difference. Okay, so I'm going to try to use the central difference formula, right? I'm going to take, so like f prime k, the kth f prime, is going to be fk plus 1 minus fk minus 1 divided by 2 delta x. Seems fine, right? If I want like my kth value here, I just look to the left and to the right of it, and I use central difference on those points. But what's the problem with using the central difference on these vectors? Yeah, there's a problem applying the central difference to the first point and to the last point. Right? So for all of the middle points, I can do central difference, because I have a point to the left and a point to the right of them. But on the leftmost data point and on the rightmost data point, I don't have f of 0, and I don't have f of n plus 1. I'm missing these data points. Okay? So I can do central difference on the interior points. And I have to do forward and backward on the endpoints. So which one do I do on which? So I do forward on the leftmost point, on the first point. And I do backward on the last point. And after this next homework, you're going to have more accurate formulas for the forward and backward difference. So we can still have second order accurate schemes for the first and the last points. Does this make sense? Right? So we just can't do central difference on the endpoints because we don't have points before and after. Okay, this is just a practicality of real data. Any questions about this so far? Okay, so the next step is to code this up. Let's say that my x's are not spaced evenly. This is a lot nicer if my x's are spaced evenly delta x apart, then this formula becomes simple. What does my central difference look like if my x's are not evenly spaced? So if, I'll let you think while I write this up, if x's are not evenly spaced, then the central difference looks like what? Fk prime equals. Okay, so the top stays the same, right? Because those data points are just called Fk plus 1 and Fk minus 1. Now, how does the bottom change? Right, so if these delta x's can change kind of variably, then really what I need to do is figure out what this effective delta x is between them, which is just x, you know, in this case it would be x3 minus x1, or xk plus 1 minus xk minus 1. Okay, so we don't need our delta x's to be evenly spaced. We just need to know what the x points are, what points our function is evaluated at also. Okay? Oftentimes, real-world data doesn't have uniform spacing in x either. Okay? Okay, so let's code this up in Matlab and see how it works on data. Okay, let's see. So I have this very similar example to the one we did last time. So what we're going to do is define x equals 0.1, here, 0.1 in increments of 0.1 to 3. Okay? And f is equal to sine of x. And now at this point, for all intents and purposes, I can treat these as vectors of data that I've been handed on a thumb drive or in an email. We know that this data has come from a real function called sine of x, but for everything that follows below, we're just going to treat x as a vector and f as a vector, just like we did on the right board. Okay? So I'm just cooking up data, and we're going to see what we would do if we just got this data. Okay? So let's just plot x and f in black, and we'll hold on. And I also want to plot x by f in red x's. So here we actually see these red x's are the data points that we've been given. Okay, these red x's are the points in the vector, the x and f points. And the black curve is the true function that these points have been sampled from. Right, so I have some experiment or some simulation, and it's following this true black curve. And at every finite delta x, it's giving me one of these red x data points. Okay? Okay, so the first thing we're going to do is maybe your boss tells you that all of the points in x are evenly spaced, or you do some test on this x vector, and you find out that all of them are evenly spaced, so you can define a dx, because your formula is going to be a little bit simpler with a fixed dx. This is our delta x. We're going to say n is the length of our data. We have n data points. Okay? And I'm going to create a vector df dx. And initially, I'm just going to fill it with zeros. I'm going to make a column vector for df dx full of zeros. And I'm just going to go in and fill this in using our formula. Okay. If there's any questions, please interrupt. So this is how we're really going to illustrate these concepts is in Matlab. So if you have any questions, please do ask. Okay, so what do we do to compute the first df dx, the leftmost derivative, the derivative at x1? Forward difference, okay? So df dx at 1, the first value, is equal to, and how do I do my forward difference? Okay, so k equals 1 here. So it's f of 2 minus f of 1 divided by dx. Right? F is a vector of data. So f of 2 minus f of 1 is the same as f of x plus delta x minus f of x, where x equals x1. Okay? For all of the central points, for all of the interior points, we're going to use central difference. So I'm going to say for I equals 2 to n minus 1. We're going to do a central difference. df dx of that index I is going to equal, okay, so what's my central difference for the ith data point? So f of I plus 1 minus I minus 1 divided by 2 dx. Okay? And then for the last point, we're going to use a backward difference scheme. So df dx of the nth data point is going to be f of n minus f of n minus 1 divided by dx. Okay. Okay, so now I'm going to make a new figure, and I'm going to plot the true solution, which is cosine, in black. And I'm going to plot our approximation, df dx, in red x's. Okay? And here we go. So this is the true derivative, this nice black cosine curve. And all of these red x's are our approximations. And it's a little more accurate in the middle because we're doing central differencing in the middle, which is a more accurate scheme. Any questions? Yeah? How many of you have done this before? Computed derivatives of data on a computer? How many of you have never done this before? Okay, good. Let's do something else. Let's add some noise to this. So down here, after I've defined the length of f, I'm going to say f equals f plus rand n. This is a normally distributed Gaussian random variable of the same size as f. Matlab's really cool. You can do really, really, really easy stuff like this. You can say, I want a vector of rands, of random numbers, and I want that vector to be the same size as my f vector. Super simple. But I don't want it to be, this will give me unit variance random numbers, so they're going to be like really big numbers, unit variance. So I'm going to make it 0.01 times rand n. Okay, so I have f plus a little bit of white noise on top of it, kind of 1% white noise. Why don't I just do this up here so we can see what it looks like? Okay, so now you see these, this is my, I messed up. Let me make this figure nicer. So I really want to plot sine of x, and then I want to plot the true data points. Okay, so you see this black curve here is the true sine, and my red dots have some error, so they're not perfectly on this black curve. Okay? And now when I run them through my derivative function, I find that I actually have errors in all of my derivatives. Like all of these red values have error, but they follow this general trend of capturing the cosine. So first of all, which of these two plots looks worse? The first one or the second one? Do my red points agree better or worse in the first or the second plot? Okay, so the red points are better in the first plot, worse in the second plot. Why? What does that mean? Sorry? I wouldn't even say squaring the error. I'm taking my error and I'm dividing it by dx, which is a small number. Right? So these are getting multiplied by about a factor of 10 because my dx is 0.1. So if you look at it, these errors are about a tenth as big as these errors. It's really more like a factor of 5, but that's bad, right? So differentiation magnifies errors, right? So if you had position data and you were trying to compute accelerations from that, you'd be in really, really bad shape because you'd be taking two derivatives, and so you'd be multiplying all of your errors by 2 dx, you'd be dividing by dx twice. It's bad news, okay? So something to be aware of, you have to have clean data if you're going to numerically take the derivative, or you have to take your red x's and do a numerical smoothing first. Okay, so later on when we talk about data methods, we'll talk a little bit about kind of curve fitting and smoothing functions and getting splines and things like that. But if you just have noisy data and you take the derivative, bad things happen. Okay? All right, I think that's it for this example, unless there's any questions about the code. Yeah?
What if we don't define line 15 of the code? What happens? Yeah.
So if I didn't define line 15 of the code, I could just, let's comment this out. And I could just add in x of 2 minus x of 1. I could add in x of I plus 1 minus x of I minus 1. I'm not sure I defined an x, did I? I think I did. And then x of n minus x of n minus 1. So I just repeat everything I have for the f's, but for the x's. Right? So I can compute dx here, and 2dx here, and dx here, even if those dx's are changing now. Okay, so this is how you would make it general. I'm a little worried about running this because I might have broken something, but yeah, it runs, and it gives you the same results. Okay, good question. All right. So this is actually a really nice segue into the next thing I want to tell you about numerical differentiation. And this is one of my favorite kind of theoretical things you can derive about numerical differentiation, is that when you're doing these operations in a computer with finite precision, there's a limit to how much you can minimize the error. There's a limit to how small and there's a limit to how accurate you can make these numerical derivatives in a computer. So if I had a forward difference scheme and I wanted to make it more accurate, what do I do? Reduce delta x. Yeah, right? It's like, that's the thing we get to change. We get to change delta x. We get to sample this thing more finely, and our answer gets more accurate, right? So if I want arbitrarily accurate answers, why can't I just decrease delta x forever? Well, a computer's not that fast, so that's a really good point. So first thing is my error scales with delta x, right? So error, we have our error scales like order delta x, but our compute time scales like order 1 over delta x. Right? Every single one of these data points, I have to do some computation on it. So if I make delta x 1,000,000 times smaller, I'm doing 1,000,000 times more little derivatives. Okay, so it's really bad for computer time. But even worse than that, there's a fundamental limit because my computer can only represent numbers with like finite accuracy. Okay, it can only represent numbers to so many decimal places before it like has no more memory to write numbers. Okay, so most of you probably know a little bit about computers. Some of you probably know a lot about computers. So how many decimal places of accuracy does a normal computer keep numbers to? Like in Matlab, if I write a number, how many decimals is it actually keeping in base 10? How many of you know the answer but just aren't saying it? Okay, so it's about 16. Okay, so one of the most common numbers you'll see in computers is 10 to the minus 16. Okay, so this is the number you're always trying to achieve in numerics, right? If your error is on the order of 10 to the minus 16, it means that you're doing as well as you can possibly be doing in a computer, unless you do really special things. But normally, a double precision number, double precision means that you have 2 bytes on the computer to represent this number. 2 bytes? More than that. Does anyone know how many bytes? 4 bytes? 4 bytes. Okay, so this equals 4 bytes, which I guess equals 32 bits. Yeah? And you get, I don't think this is right. I think this is 8 bytes. Anyway, you get 52 binary decimals of accuracy. Maybe I'll do a whole lecture on what your computer's doing at some point. But for now, you can basically, the upshot is if I have some number in Matlab, if I say 5 plus 10 to the minus 17, Matlab really thinks the answer is exactly 5. It doesn't know how to have a number as big as 5 plus something as small as 10 to the minus 17 in the same number. It just can't represent that number as any different than 5. So its answer is exactly 5.000 ... 16 decimals O. Okay? So what this machine precision, this is called, we sometimes call it like epsilon, which is machine precision. This is the limit of how close your computer can tell different numbers apart. If you type 1 plus 10 to the minus 17, it doesn't know that that's different from 1. It can't tell any difference. Okay? So the idea here is every number that you ever represent in a computer is going to have round-off errors. When you write pi, it's going to spit out a bunch of digits of pi, but it's not exactly pi. It's about 10 to the minus 16th off from the true value of pi. Same thing when you write down square root of 2 or e or any not nice number. It can actually exactly represent numbers like integers and 1/2 and things like that, but any weird number like square root of 2 or e or pi is going to have this built-in round-off error because the computer just can't represent it perfectly. Okay? So now we're going to take this idea of round-off error, and we're going to plug it into our finite difference derivative, our forward difference scheme. And we're going to find that as we decrease delta x, our approximation gets better and better and better until it starts magnifying this round-off error, and then it'll get worse and worse and worse. Okay? So let's say df dt is equal to f of t plus delta t minus f of t divided by delta t. Okay? But really, every number in here has some error associated with it. Okay? And for right now, I'm going to assume that these numbers were perfect, and it's the computer that's messing things up. So there's some little epsilon machine precision on this and this and this. Okay? Now, I'll let you work this out, but really, the only epsilon that matters is the one in the numerator, because it's getting divided by delta t. And so what we have is f of t plus delta t minus f of t divided by delta t plus error divided by delta t. This error is machine error. Okay? So there's 2 different ways that error can enter into this calculation. One is through this kind of Taylor series or finite difference approximation error. So this is equal to f prime plus order delta t error. This is from essentially Taylor series. Plus this epsilon over delta t error, which is from machine precision. Does that make sense so far? Right? Every time you enter a number in Matlab, there's some little kind of round-off fudge error that is introduced in that step. And if delta t is too small, you actually make that round-off error look really big. If you divide by a really small delta t, this number starts getting big. OK, are there questions before I move on? OK, so essentially what this looks like is if I had a plot of error versus delta t, so this is kind of total error, both of these terms, right? These are both my error terms. The sum of all of my errors, both from the Taylor series finite difference errors and from this machine precision errors. If I start with really, really big delta t, like the delta t's that we're using in the examples are like 0.1 or 0.01. Those are pretty big compared to 10 to the minus 16, right? Like what's 10 to the minus 16 divided by 0.1? 10 to the minus 15. Still super, super small. Way bigger than order 0.1. Okay? So for really big delta t, most of my error is coming from this Taylor series. And I start with a big error from the Taylor series. As I decrease delta t, this error gets smaller, while this error starts to get bigger. But this one is so, so tiny that for a while I actually get much better, much less error as I make, sorry, this is delta t smaller. This is 1 over delta t. Okay, so we're making delta t smaller in this direction. Okay, so as delta t gets smaller, my error gets smaller for a little while, actually for quite a while, until at some point this error has grown large enough that it's now the dominant error in this expression, and every time I decrease delta t, this one gets bigger and bigger and bigger until it eventually starts to dominate. So there's really this kind of optimal delta t that really does minimize this error. Okay? If you compute this, I'm not going to go through the details, but you can actually do this from the lecture notes. You can take this error expression and you can take partial error, because error is a function of delta t, right? I can take partial of that with respect to delta t, and I can set it equal to 0, and I can actually find v delta t where I have 0 slope in the error, my minimum error as a function of delta t. And for a forward difference scheme, it turns out to be about delta t equals 10 to the minus 5. And that's because these terms really have some constants out front that we can kind of characterize. But so this is about 10 to the minus 5. So if you're doing forward difference, you can't really do that much better than 10 to the minus 5 or 10 to the minus 6 for delta t. And if you try, things will start getting worse. And now you know why. Okay? Other schemes are better. If I had a central difference scheme, then I might be able to go much lower in error and for a much smaller delta t. So other schemes you can get lower error just because this starts off being much smaller. Okay? That's all I really want to say about finite difference differentiation unless there are questions. This is really important stuff. This is going to be, so this is not just if my boss emails me a vector of data and tells me to take the derivative, which happens more often than you would think. these basic formulas, approximating derivatives, and in the next section we'll see approximating integrals, are going to be the basis for how we numerically integrate ODEs. Okay, so what we're going to see soon is that we have ODEs like df dt, let's say dx dt equals some nasty function f of x. Remember, this is what we've been doing for the last few weeks. We have some ordinary differential equation where x is some trajectory in time that satisfies this equation. Maybe it's the population dynamics of bunnies or radioactive decay or the motion of a spring on a mass. But in a computer, I'm going to have to use some approximation for dx dt. So if I use forward difference, I would say, okay, well, this is really xk plus 1 minus xk divided by delta t equals f of, and I'm going to have to plug in some real finite value for x, let's say xk. Okay? And so if I take this to its logical conclusion, right, I multiply both sides by delta t, I add xk, and I get this expression, xk plus 1 equals xk, my current state. So my future state is my current state plus delta t times f of my current state. We just wrote an integrator. This will integrate your ordinary differential equation. You give it x naught, I can give you x1. Now you have x1, I can give you x2. Now you have x2, I can give you x3. This is an iteration that steps your differential equation forward in time. This is called an integrator. Okay, we have just integrated this differential equation and found an approximate vector x, which represents the trajectory of x in time. This has error associated with it because this has error associated with it. So at every time step, we're picking up error, and that's a bad thing. Okay, so on Friday and in the next week, we're going to be talking about these types of problems, these integration problems. So it's really important that we understand these basic finite difference derivatives, where the errors come from, and what these things look like in a computer. Okay. Before we do this, I want to show you how to do numerical integration of data. Okay, we just took the derivative. Now we're going to integrate. We're going to add up f of x. And we'll probably get through about half of this today and the other half on Friday. And then on Friday, we'll kind of go farther with this numerical integration of ODEs. Okay. Okay, so this should be kind of maybe a little bit of a simpler week than before, because before we were dealing with nasty ordinary differential equations and phase portraits and geometry. This week we're doing calculus, right? We all know how to integrate functions and differentiate functions, and this is pretty familiar to us. So if I have some function f versus x, what are some ways that I can compute the area of this, the integral of f with respect to x? What's the way we learn in a calculus class? So yeah, you can add up little bars, little rectangles, right? I can chop this up into a bunch of dx's and add the height and the area of those rectangles. There are some other interesting ways. I think Archimedes did this with triangles, which seems bizarrely difficult to me. I think rectangles is way easier than triangles, but you could do it with triangles. So I could chop this up into a bunch of rectangles like this, and I could add up the area of all of these rectangles, right? This is the Riemann integral. How many of you have heard of Lebesgue integrals? Okay, it turns out that the Riemann integral we learned in calculus is not the only integral. This is kind of a matter of convenience telling you that there was only one integral, but there's definitely more ways to integrate this. So if I had a nasty, nasty function that had delta functions, if I had a finite number of delta functions in my function, this happens sometimes, my Riemann integral is going to blow up. Like, I don't know how to handle these delta functions using vertical bars. I just don't know how to do it with Riemann integrals. It turns out that there's something called a Lebesgue integral. It's spelled weird. It's spelled like Lebesque, but it's called Lebesgue. And it's called the layer cake integral. So instead of integrating with vertical bars, you integrate with horizontal bars. And you take the limit as delta x goes to 0. And it's much easier for handling these finite discontinuities in your function. Okay? Not something you need to know about, but in general, you should know that there are other types of integrals, and you could formulate this in other ways. And there's like a whole very important theory of probability built on Lebesgue measures instead of Riemann measures, ways of measuring area. Okay? So our integral of f with respect to x, so f of x dx, we're going to give it some limits of integration. We're going to integrate from a to b. Okay, so I'm going to write down this formula. It's always a pain to derive it, on the spot, so I'm going to write it down. So essentially what we're doing is we're going to take the limit as these rectangles become very, very small, which is the same as saying I'm taking the limit as my number of rectangles approaches infinity. Okay, n is the number of divisions or rectangles that I'm going to put in here. And this is the sum of all of my rectangle areas. So for k equals 1 to n, I'm going to add up all of my rectangles. And the rectangle height is just f at that value x. So f of a plus b minus a divided by n times k. So the kth rectangle has a height of f of that x, and that x is a plus b minus a divided by n times k. Think of this as my little delta x. b minus a divided by n is delta x. So this is the height. This is, delta x. And then I take this height and I multiply it by the width. What's my width of one rectangle? Right, it's my delta x. It's b minus a divided by n. Okay, so this is my kind of formula, my Riemann integral. I could do this, take the limit as n goes to infinity. I have infinitely many rectangles. This delta x goes to 0 because I'm dividing by something that's going to infinity. And this is my Riemann integral. But just like we did in finite difference derivatives, we're going to stop here. And we're going to have a finite number of rectangles. We're not going to take the limit as n goes to infinity. We're not going to make these delta x's go to 0. We're really going to add up finitely many rectangles, because that's what we can do in a computer. So this is approximately equal to this for a finite n. So what I've drawn here is actually a right-sided rectangle rule integral. This is a little bit of a esoteric. It's actually kind of practical. So I could define the height of my rectangle using the left point of that interval or the right point of that integral. So I could use this height, or I could have used that height. And this function up here is using the rightmost point of my rectangle to get the height. I could also use the leftmost point like I've drawn here. Okay, so this is really a right-sided rectangle formula. And if I wanted the left the left-handed rectangle formula, it would be this limit. I'll get to that later. You could get another expression for it. I don't love this formula because it's really nasty and complicated. Okay, there's a lot of moving parts, a lot of terms. I don't like this formula. It's too complicated. So let's make it way, way simpler in terms of vectors of data. So let's give these things names. So what I really want to think about is this is some x0, x1, x2, up to xn. Okay? And this point is f of x0. We're going to call that f0. F of x1 is f1. This is just like we did for the finite difference derivative. We're just going to call these x0s to xn's and these f0s to fn's. And now our integral becomes way, way simpler. So now we have the limit as delta x goes to 0 of the sum from k equals 1 to n of f of xk delta x. Much simpler. And again, for numerical calculus, we just get rid of this limit, and we have a finite delta x. If my delta x's were variable, I would just have xk minus xk minus 1. That's my variable delta x. Okay, so n is the number of rectangles. Delta x is the spacing, kind of the width of all of those rectangles. And this is the height of kind of the right side of these rectangles. Any questions about this formulation so far? It's a little messier than the derivative, but when you write it like this, it's actually pretty simple, right? So what we're going to do in the next lecture is we're actually going to approximate how different this expression is. Sorry, let's get rid of this because we're going to do this in a computer. We're going to see how different this approximate numerical integral is to the true actual integral. Again, using Taylor's series and getting orders of error in terms of delta x's and things like that. So we're going to get the same types of formulas for what type of error our integrals have using Taylor's series. And then we're going to learn how to code this up in Matlab and cook up a couple of better integrals. The left and the right rectangle rules stink. So we'll have much, much better integral formulas kind of later in the next class. OK, that's all for today. I'll see you again on Friday. And then next week we'll do ODE integration.